In this lecture, we are going to go over how to do dimension reduction, specifically by using a principal component algorithm. Now, before we get in, I want to conceptually try to explain dimension reductions in two different ways. The first way I'm going to try to explain it is using this 3D model. Now, this 3D model, let's just pretend like it has these three dimensions. What a dimension algorithm would want to do is, let's say like we have three dimensions. We have these three dimensions: petal width, sepal length, and sepal width, and we want to only have two dimensions. What a dimension reduction algorithm is going to do is it'll rotate this around until it finds whatever angle captures the most amount of variance in the data. And then once it finds that angle, it will create new dimensions. It'll create one dimension. Let's say like if this, for instance, captures the most amount of variance in the data, because we can see the points as spread out as most as possible, it'll create a new dimension going this way, and then a new dimension going that way, and it will then assign each one of those points along these two axes. And we'd get rid of all the other dimensions that we have, and we could then use those two dimensions. Um, and that is one example of how dimension reduction works. And what I mean by variance is, for instance, if we were to just look at here, this doesn't capture very much of a lot of the variance of the data because all the data is smushed together. What the dimension reduction algorithm will want to do is spread this data out, find the view that would spread this data out as much as possible. So that is the visual point of view. Now I'm going to give you more of the computational explanation to what dimension reduction does. So let's say I have this data here, and this is one of the most common use cases, I'd say, for dimension reduction. Um, let's say I have this data here and I want to perform a regression analysis on it. So this is housing data. I have prices, which would be my target variable. Then I have the number of bedrooms, the number of bathrooms, the square feet of the house, as well as the square meters. So right now I have four different dimensions or four different features. If I go ahead and I try to use a dimension reduction algorithm on this, use a regression analysis on this. I'm going to input my Y range as price and my X range as these different features right here. And then I want to have labels. I'll have my output range. I'll just select that right there, and I'll run my regression analysis. And let's look at these coefficients. Now remember, what these coefficients mean is, the way I interpret this is for every additional bed I add to the house. Let me go ahead and put commas in here to make this. So the way I interpret this is, for every additional bed I add to the house, the value of the house goes up by $53,000. However, if I look at baths, for every additional bath I add to the house, the value of the house goes down by $25,000. Now with square feet, according to my regression analysis, every additional square foot I add, my house goes up in $12,000. However, for every additional square meter I add, my house goes down in value by $128,000. So if you just think of the intuition for this does not make sense at all. Why is it that, how is it possible that adding square feet to a house increases the price, but a house with more square meters decreases the price? Well, the problem comes down to something called multicollinearity. And what's going on here is are both of these variables are highly correlated. In fact, they're perfectly correlated with each other. As square feet goes up, then square meters goes down. What this does is it throws off what the coefficient should be. For instance, if let's say like for every 1 foot, the price for every, I'm going to make something here, for every foot, the price then increases by 3, so price will equal 3 times feet. And I have this function here, and I have 1 foot, 2 foot, 3 foot, 4 foot. I do that. Okay. Well, that's great. However, if all of a sudden I add a new variable in here, let's call this let's call this meter, and meter is, let's just say the meter is 3 times as much as feet, and then I force meter to be a part of this equation. Well, how am I going to do this all of a sudden? Something I could, if I can't just leave it to be 3 plus whatever meter is, because that gives me a different number. So perhaps something I could do is, I don't know, I could do meter times 2. If I do meter times 2, and then I do square feet minus 3, if I do that as my equation, all of a sudden you see that my price stays the exact same. However, if I look at my coefficients now for feet, it's -3 times feet plus square meters times 2, and that gives me the exact same price. So what the regression equation is doing is it's trying to figure out a way how to fit in all these variables and then still predict the price. However, by fitting in more variables, while it's starting to create a black box here where all of a sudden these coefficients become meaningless. We know that essentially price goes up 3 times the rate that length goes up. However, by adding multiple variables, all of a sudden that makes the coefficients, it will try to put the coefficients to wherever they need to be, just so it can equal that price and the coefficients become meaningless. And that is what we're seeing here. And that is one of the main reasons why you'd want to reduce the dimensions of a data set. So I go back here, for instance, I have square feet and I have square meters and I have bedrooms and bathrooms. What a dimension reduction algorithm could hypothetically do is I'll copy this data. Here we go. I'll copy our price data over here, and then I'll take this data. What it might do is it might say, well, since square feet and square meters are both so highly correlated, we are just going to take square feet. Then what it's going to do is it's going to look at, okay, well, bed and bath are also very correlated. What if we just create a new variable called room, number of rooms, and that is going to equal the sum of the bedrooms and bathrooms. And so then I have this new data set here with reduced number of features. So the algorithm looked, it saw that since square feet and square meters are so highly correlated, it just mushed them together. And then same thing for bed and bath, it found some way to mush it together. So now that I have this new data set that our dimension reduction algorithm was able to work on, let's see how this comes out with our regression analysis. So I'm going to go back to data. I'm going to go back to data analysis, go to data analysis. I'm going to run regression. Here we go, select price as our input variable, and then our features as our output. I'll output it right there. And now if we run our regression analysis, we see that for every additional square foot, let me convert this to dollars. For every additional square foot that is added to a house, the price of the house goes up by $175. And for every additional room added to a house, the house price goes up by $52,000. And that's much more reasonable. And that's what we're actually looking for. And that makes a whole lot more sense than this regression analysis we had over here, where we get negative coefficients for something like square meters. So that is one of the primary use cases of why you'd want to see why you'd want to use dimension reduction to be able to extract those features. That's very common. The other use case is just being able to display data on 2 dimensions like this. But those are the use cases for dimension reduction. In the next video, we are going to go over how to actually use a dimension reduction algorithm.